This is homework 1, part B. So part B's question is asking, derive the time-dependent material and energy balance equations of the CSTR described, which is the table that's provided from the textbook. Then code, solve, and plot the time-dependent concentration and temperature profiles for the CSTR when the coolant temperature, or TC, is increased to 305 Kelvin at when the time is equal to 0. So, we're just going to be focusing on deriving the time-dependent material and energy balances. So, I already went and wrote the starting ones up here. These two equations that I have here, this is the material balance, this is the energy balance, and this is the material and this is the energy balance for a continuously stirred tank reactor, or a CSTR, that is not at steady state. So, we're first going to do the material balance one. So as we can see here, we have the dV, I can't speak. We have the derivative of volume times concentration over the derivative of time, or with respect to derivative of time, equaling the flow multiplied the concentration going into the tank minus the concentration in the tank, which that whole part is then being subtracted by the volume times the K constant, or the K value, not K constant, excuse me, the K value times the concentration in the tank. So from here, something that I can already see that we can already do to start getting this to derive it to the right equation that we need. We know that the tank's volume is going to be constant. It's not going to be changing. It's not going to be changing the volume or the size of the tank itself. So the volume is not going to change. Therefore, we can take that V out of that derivative, so that way then we just have the derivative of the concentration with respect to the derivative of time with V on the side. So let's do that. So we're going to have V and then dCA dt then equal to Q, concentration going in minus the concentration inside the tank minus the volume times the K value times the concentration in the tank. So now we're here. Now I think we can obviously see a clear path of what we can do next. So we're going to take the V from this side of the equation and bring it over to this side. So then we can just have the dCA over dt on this side only. So when we do that, we actually do this obviously, so let me write it out. So we're going to have dCA, I'm sorry, that doesn't look good. We're going to have dCA over dt, it's right here, is going to be equal to the flow over the volume of the tank. So Q over V, and then that's just multiplied again by that concentration going in minus the concentration already in the tank. And then that's going to be minus, since we're dividing this by V, we also divide this by E. This already has a V in there, so it will cancel out the volume, at least for this section right here. So then we're just left with the K value times concentration, which I also already had it set to where it's the K value times the concentration, as it's just the general rule that RA is equal to the K value times concentration. So I basically already went, because technically RA would have been V times RA, and so I just already went and just substituted that in for the problem. But just want to note that that is what this is. So yes. So then from here, we now actually have the problem set up to where we're looking for the change or the derivative of the concentration with respect to the change in time is equal to flow divided by the volume multiplied by the concentration going into the tank minus the concentration of the tank, which that's being minused by the K value times concentration. So we have that. And I also wanted to note as well, another little side note, the K value also is solved by doing the equation for it, which is K naught raised to the power of negative T. I just want to make this distinction here, as in the table that is provided to us, they give us the parameter of E over R, which is this E over R that's used to help you find K. And when we actually go out to do the coding and actually show like the, when we do all the coding for this, we're gonna just simply do it to where we put the value for the E over R that they provide in that parameter. That's gonna be divided by the temperature that's listed in here as well. So just want to say, not listed in the table, but the temperature that's given for the problem. But yes, so I already mentioned that there. So now we're going to move over to the energy balance. Again, this and this problem, those are general material and energy balance equations for a CSTR at an unsteady state. And so we're going to then derive this to get it to an equation that will kind of work better for us. So I'm going to kind of do the same approach where I did over there, where I was kind of seeing, is anything constant? Is there any constants that we can already kind of like see here to help us already kind of get to what we're trying to get, which is in this case, the derivative of the temperature, or the change in temperature with respect to the change in time, or the derivative of time. So I can already see that density, the heat capacity, and volume. Volume, like we stated before for the material balance, that's constant, that's staying the same. But we also know the heat capacity is going to be staying the same as well, and the density is going to be staying the same. So we can then be able to pull density, heat capacity, which I just put C, not CP, because it was just too much to write. But C and the volume, we can take that out of this derivative equation. And so then we just have dt over d capital T over d little t, or the change, or the d temperature over the d of time. So when we do that, we get this. Excuse me. And now that we have that, we actually can get somewhere with so now we're going to take this from the left side and we're going to move it over to the right side like we did with the material balance. So and then we just have dt temperature, change in temperature over change in time with respect to change in time. So that will then look like this. Density and heat capacity will cancel out, but we can't cancel out the volume. So we're going to have the flow over volume multiplied by the temperature going in minus the temperature of the components or the content, and then do this. We're keeping our K and our CA value. We can get rid of the volume as that's already here, but then we don't have anything to cancel out the density and heat capacity, so that's going to be divided by this section here too. So then we have this divided by density and heat capacity. And then lastly, this, excuse me, sorry. We don't have any density, heat capacity, or volume that can be canceled out over here. So this is going to be, UA is going to just be divided by density, heat capacity, and volume. And that's going to be multiplied by the temperature in the content of the components minus the coolant temperature, which TC, which is the coolant temperature, is the temperature that's in the cooling jacket around this CSTR, which in the problem it was stated that it's 305 Kelvin. But yeah, so here we go. We have, we derived our equations for the material balance and for the energy balance that will allow us to be able to go and plot the time-dependent concentration and also the time-dependent temperature profiles for this CSTR. So now that we have that, we can go to the Python and code that and show that out. Okay, so now we're doing part B of the Python coding for it. So again, the question said derive the time-dependent material and energy balance equations of the CSTR described from the sample table data that was given from the textbook, which we already did in the whiteboard section. And now I'm going to code, solve, and plot the time-dependent concentration and temperature profiles for the CSTR when the coolant temperature, or TC, is increased to 305 Kelvin at time equals 0. So I think what we're going to do to start is we're going to list out all our givens, which is everything in the table. So give me a minute to get all that in here. Sorry if this is awkward. I'm just currently trying to type all this in. I don't really know what to say right now. I don't know why I'm like spacing those out so much. They just need to go. So let me, oh my gosh. QCI, TI, and then V equals 100 liters. And then we have density, aka rho, which is equal to 1,000 grams per liter. And we have heat capacity, which is equal to 0.239. And then that is joules. Sorry. Joules over grams times Kelvin. And then we have a negative HR which is 5E4 joules over moles. And then we have ER, which ER is used to find K. And in this case, they already did E divided by R for us, which is what this 8,750 Kelvin thing is. So when we do K, we're just going to do K equals K naught times, or to the power exponential, to the exponent of ER, negative ER divided by T. So, but anyway, so we have K naught, which is equal to 7.2 e to the power of 10, and that is 1/minute. Then we have UA, which is equal to 5E4, which is joules over minutes times Kelvin. Then we have the coolant temperature naught, or TC naught, which is 300 Kelvin. Then have concentration naught, which is 0.5 at moles per liter. And lastly, we have temperature naught, which is 350 degrees Kelvin. Okay, so we put all the givens in. Let me double check to make sure I put it all in there correctly. I'll be very sad if I mess up one of them and I don't peep it. It appears that I do. Okay, so the only other thing I'm going to put in here is the coolant temperature that they want us to get to, which is 305 Kelvin, which this is what we will be, this is what this whole problem, this is what we're looking, the concentration and temperature profiles for the CSTR at when the coolant temperature that's going through the cooling jacket, that's cooling and chilling down the actual CSTR itself, and seeing how that, when that value goes from 300 to 305, aka you're increasing, the temperature, aka there's less cooling happening to the CSTR. What will that do to the concentration and to the temperature profiles? So, shift enter, perfect. So now we're gonna go and define a function. So We'll just call this right-hand side because I don't really know what else to call it. And then our independent variable is time. And then we're going to do our dependent variable as a vector because we have two dependent variables in this problem. It's concentration and temperature, as they both are dependent upon the time in this problem. I don't know what I was trying to, there was nothing else to allude to that. That's just what it was. So yeah, okay. So then this will be equal to the vector. So now we're going to do the K. Oh my God, I'm so sorry. Excuse me. Ooh, okay. I feel like I had to sneeze. So K is going to be equal to K naught, which we already have as a given, to the exponential of negative ER divided by T. All right, and now we can return. And our return is going to be the two, final equations that we got when we actually did the full material balance and the full energy balance, which are these ones down here, because we're looking for dCA over dt and d temperature, d concentration over d time, and d temperature over d time. And because that's essentially what the find function that we're doing is. So I'm going to do this. So we're going to have Q divided by V, and then that's going to be multiplied by CAN and then that's minus CA. And then that is minus K times CA. And then we're going to do the other one, which is Q divided by, big V which, I just realized, so concentration in is the same as concentration I. I should have specified that, my apologies. But yes, so CAIN or CAN is CAI, or initial concentration going in. So anyway, back to what we're doing. So Q divided by V, which is then multiplied by the temperature going in minus the temperature of the components. And then that all, because let's see here. So we have QV times that, and then that is being added to negative HR, which for me, I'm going to do this so I can better keep track of everything. So negative HR times, oh my gosh, what am I doing? I'm so sorry. I don't know why I just did that. That is so random of me. Negative HR times K times concentration, and then that is divided by rho times the heat capacity. And then that is being subtracted by UA divided by rho times the heat capacity times the volume, and then that's being multiplied by T minus TC. Okay, So there we go. I want to make sure I have this equation correct because there's a lot going on there. Let me put that up there. So Q divided by V times the concentration going in minus the concentration already in the tank. And then that all is minus K times concentration. And then, oh my gosh, stop it. And then we do Q divided by V times temperature going in minus the temperature already in the CSTR. And then all of that is being added to negative HR times K times CA divided by rho times heat capacity. And all of that is being subtracted by UA divided by rho times heat capacity times volume. And that is being multiplied by T minus TC, which I just realized, just to make sure that nothing gets misconstrued. There we go. So that way then, we're saying that rho times heat capacity times volume, that's being multiplied and that's being divided by UA, and then all of that is being multiplied to temperature minus TC. And let me make sure that same logic is applying with the other ones as well. Yes, yes, okay, good. And then, yes, well, let me go and just, I'm a worrywart, and so I like to make sure that everything is like going to work accordingly. So okay, perfect. So now we have the function defined. So now let us do solve underscore IVP, which this is nothing new for us. I post, oop. Does that work? Does that make it better? No? Oh, I'm silly. Okay, there we go. I was like, something's wrong with that. I don't know what it is. Okay, so solve IVP. We know that, so the function, right-hand side. Then, we're gonna do 0 to T end. Let me quickly go and just do T end equal to like 100 minutes. There we go. And then we need so now, okay, sorry. I am not okay, so sorry. So as you can tell, again, we have two dependent variables, concentration and temperature. And again, with solve IVP, you have to have your function defined, then you set your time limit or the time span that you're looking at, and then you need the initial variable of the dependent value that you're looking at. So then from there, then we do method equals, how do you spell raw do? How do you spell raw do? Oh my gosh. Okay. Sorry, I forgot how to spell raw do for a second. And then we do dense underscore output equal true. Perfect. And now we have our solid IVP. And again, just like we do before, we could look and see, oh, and let me set this equal to like that. There we go. And then we could do like, and do a random time like 4 seconds, and then we get what the concentration is and what the temperature is at that value. Something I do want to also kind of mention is that if we were just to look at the right-hand side and look at CA naught and T naught, never mind. It's not going to work right there. I think I'm missing a step. So let me first like get the other part done before I like start jumping steps. So we need to do MP dot line space 0 T end, and then we'll do like 200 points. I think that's fair. And then we're gonna do CA T is equal to res dot sol, and then we put in our T plots, and then we're perfect. Okay. I wonder if now this would work. Nope. Okay. I think you could tell what I'm trying to do, but I might have to come back quickly and see what I'm doing wrong. But we'll get to that first. But so now let's go and make the graph. So we need fig make underscore subplot Oh, no. I did not mean for that. Oopsie. Dang it. So then we're going to do x equals t plot. Then y equals t. And the name is equal to t. And then do fig dot add underscore scatter. And then we're going to do again x equals t plot, y equals CA, and then we have name is equal to, oopsie, CA. Okay, give me one moment. I need to see what's happening here, because give me one moment. I'm going to see what's going on with this. Okay, so I'm back. I figured out what the problem was. I forgot to add in rows, which is 1, and then columns, which is 2. And then go here and do row equals 1, column equal 2. Oh, no, I meant this is V1. And then do row equal 1, and then column equal 2. Oh, what's going on? Oh, yes, okay. There we go. And then I just need, what happens if I just, it's 800, and then the height will be like 500. Give me one moment. I'm going to see what... Give me one moment. I'm going to see why it's still doing this. Okay, so I'm back, and I figured out what the issue is. I need to change the minutes, because right now it's reading for 100 minutes, and that's why it's so jarring. So we're just going to look at a smaller section of the total time. In this case, we're going to look at 10 minutes. So here we are. So as we can see, as we can see, the CSTR for the concentration and temperature profile, when we increase the cooling temperature of 300 Kelvin to 305, this is what they end up looking like, with this being the temperature, I'm trying to think of the word, profile, and this being the concentration profile. Now, some things that we can kind of like take away from this. I mean, obviously, the main explanation behind why it's doing this type of oscillation is due in part to the fact that, we're basically increasing the coolant temperature. And as you know, with reactors, usually they have a cooling jacket, and a cooling jacket does what its intended purpose, what the name of it is that it's meant to cool the reactor down. It's a jacket that goes around the actual reactor and it cools it. And in this case, we're increasing it by 5 degrees Kelvin, and from 300, which we can look quickly, if we have it at 300, it's, you would expect that these graphs, if it's at 300, which technically should be at steady state, or at the original steady state, that this would be plateau. It would be flat. But there is this kind of dip, and the same thing with this one. And that is due in part that the authors who gave us these numbers didn't give us the full number down to the exact decimal. So because we didn't get the exact decimal of the number, we're not going to actually get like the exact steady state profile. I mean, we can get very close, like with what we are observing here, but we're not going to get exactly that steady state. But bringing this back to 305, this oscillation is occurring because, again, we're increasing that cooling jacket coolant temperature from 300 to 305, and with that, the reaction is being chilled less. Therefore, it's allowing that temperature of the reactor in general to go up. And because the reaction of because the temperature of the reactor is going up, that's then making the reaction occur quicker. Therefore, then, because the temperature is going up, therefore making the reaction occur quicker, concentration, as a result, is going to go down quicker because the reaction's happening faster. So it's going through more of the concentration. And then when the concentration hits these low points, or specifically in this case, the low point, we'll then see that, well, there's less concentration, therefore the reaction will start to slow down, and therefore then the temperature will start to come down as well. And as the temperature is coming down and the reaction's coming down, the concentration is then able to kind of go up again, as we see here, as it's starting to go up when this was kind of starting to plateau, or not plateau, but start to dip down. But again, as the concentration started going up, then the reaction was able to start reacting quicker again, therefore then increasing the temperature. And that's how we kind of get these oscillations. And I guess you could then have that same logic be, well, if we increase the temperature more, shouldn't we see more oscillations or the same type of phenomena to occur, if not bigger oscillations? And I don't know, we can check and see. That seems to not be the case. It seems to be the case that we have that initial first jump, where the temperature rises, therefore then the concentration falls, therefore then the reaction falls, therefore the temperature falls, but then it starts to just kind of plateau. And this is a really prime example of, not only just using simulations to show this, because imagine having to do this in an actual reactor and you're like, oh, dang it. They're not going to do that. It's also just the case that it's showing that there are just some critical temperatures that cause consistent oscillation. And in this case, we could look at 307. And yeah, we can see that at 307, it does follow that trend of where it jumps again and then it goes down, and it's, doing the same thing with the concentration, with the temperature, but it naturally has these oscillations that are just starting to die down. Like they naturally fizzle out and, plateau. And we can even check at 303. And yeah, it starts following the trend. It does it. It starts looking exactly like when it was at 300, where, you just have this initial jump, this initial dip down, and then it starts to plateau and, go consistent. So that is kind of the general understanding when it comes to the concentration and temperature profiles for the CSTR when you are changing that coolant temperature in the cooling jacket. As you know, the cooling temperature will affect the temperature itself of the actual vessel, and therefore, temperature can help drive reactions to go quicker. I mean, or it's a result. It's the exothermic. Let me take that back. Let me backstep because I misspoke. Temperature and the increase in temperature and the rise in temperature is not only due in part because that coolant temperature is increasing, therefore it's increasing the temperature in general of the reactor because it's not as cool as it was before. The temperature is also being increased due to the fact of the exothermic release that's happening from the reaction, which is occurring because the concentration is being used because the reaction's happening quicker, therefore it's giving off more temperature or more heat. So, but yes, that is generally the concentration and temperature profiles based off of that time, with them being time dependent. And that's generally kind of how they relate together. So, yes.